Okay, let's start our lecture. So good afternoon. So the tutorial start this week. Yesterday we have 2 tutorials. Some of you have already attended the tutorials. Remember to work on the tutorial problems before you go for your tutorial. For those who have not registered for tutorials, let us know. Okay. There seems some problem about online registrations. Anyway, if you have not registered, let us know. I told you there are some reserved tutorials, but it seems that they're not that popular because most of you have already registered. But if you find that you are in a tutorial group that are too crowded, if you want to transfer to other tutorial groups, let us know. All right. Okay. So last week we talked about conditional probability. It's a very important concept. So the idea is that if you are told that a particular event has occurred, then what is the probability of an event being occurred? Will it still be the same or will it be different from without the information of this second event occurred? Gee. Okay, so let's look at this example 7 on page 212. Example 6, you can read it yourself. So 212, page 212. Okay, now, so this statistics professor teaching both morning and afternoon sessions for introductory statistics course. All right, now there are 2 events mentioned here. The first one, I call it A, is that this professor gives a bad morning lecture. Okay, B is the professor gives a bad afternoon lecture. It's not a good example. First of all, we should be more positive, so you talk about good lecture, all right, in both morning and afternoon. All right, okay. Now suppose that the chance that it gives a bad morning lecture is 0.3. Not that bad and not that good. It's supposed to be 0. All right, but it's 0.3. Probability of B, 0.2. Slightly better. Maybe after lunch it's getting better. All right. So the probability of A and B equal to 0.1. So all this referring to the same day. So for the same day, both morning and afternoon lectures are bad. So the chance is about 10%. Right. Now you have to remember, probably A intercept B, because A intercept B is a subset of A and a subset of B. Therefore, this number must be less if you remember the properties of this probability. So this is a subset of A, therefore this probability must be less or equal to this probability. This is a subset of B, therefore this is less or equal to this number. So if not, then this is not a well-defined probability, all right, or some mistake somewhere. All right, so now we want to calculate the following probability. First one, given that we know that the morning session is a bad lecture, then what is the chance that the afternoon is also a bad lecture? All right. So we also would like to know what is the chance that if the morning is bad, then the afternoon is not bad. What is the probability? Or probability of A given B given A complement, and probability of B complement given A complement. All right? So, follow from the definition, this one is equal to probability of A intercept B divided by probability of A. All right? So, we know both, so we can calculate this easily. So, this one, the B part, follow from the definition, then it's probability of A intercept B complement divided by probability of A. But what is the probability of A intercept B complement? All right? How to get this one? It's not given, so we may have to work it out. After you work out this probability of A intercept B complement, then you just take the ratio and then you will get the answer. But there may be an easy way out to get part B answer. Both A and B are conditioned on A, conditioned on the same condition. Event A has occurred. So B and B complement should add up, okay, or in other words, these two probabilities should add up equal to 1. These two should add up equal to 1. So in other words, this one can be written as probability 1 minus probability of B given A. All right? So let me repeat it. They are both conditioned on the same conditions. That is, event A has occurred. This professor gives a bad morning lecture. All right? Then, whether afternoon is a bad lecture or good lecture, these are complement events of each other. All right? So it's 1 minus it. So this second approach is easier because we just get the answer from A and then subtract it from 1 and we got the answer for B. Instead of getting the probability of A intercept, B complement intercept A. Okay? So I told you, don't just happy with one way. Try to figure out how to get the probability of A intercept B complement. So, I have set up equation. If you remember, what can we say about A intercept B and A intercept B complement? Look at these two. What is the intersection of these two? A, B, S, empty set. Yeah, like multiple choice, right? The fifth one is I don't know. All right. So, what is these two? The intersection of these two. Empty set, A, B, or S, or I don't know. The answer is obvious. Obvious to me. The two, okay, you see B complement in one set, the other one is B. How can you find something common to B as well as common to B? How do you find an element common to B and common to B complement? No such thing. So the intersection is empty set. How about union? We put them together, that's A, because it consists of those belong to A and B, and those belong to A but does not belong to B. So when you combine them, union them, it is A. So this is just A. And they're mutually exclusive. And the intersection is empty set, therefore the probability of A is equal to probability of this plus probability of this. We know what is probability of A, what is probability A intercept B from what we are given, so we can calculate this. All right. But you need to do a few more steps in order to get the answer for part B. All right. So this just to illustrate that, yes, try to think of different ways to get the answer, all right, and able to explain why each way works, all right. So here we have two ways to do it. Okay, the third one, probability of B given A complement. Oh, can I just 1 minus probability of B given A? Right? Is this correct? Why not? A and A complement, A and A complement together is the sample space. All right? No, it's wrong. They basically condition on different conditions. The first one is condition and A has occurred. The second one is condition on A does not occur. There are two different conditions. So no way that you can link them together. I mean, not so straightforward. All right? Unlike A and B together end up equal to 1. Because they're conditioned on the same thing, so B and B complement together, all right, is the whole sample space. Since you condition on A, so basically it just becomes A. All right? Or equal to 1, what I mean is equal to 1. The C part does not equal to 1 minus probability of B given A. All right. But how about these two? These two add up equal to 1 because they condition on the same conditions, A complement. The professor, all right, gives a good lecture in the morning, so what's the chance that it got a bad lecture, or what's the chance that it gives a good lecture? All right. So how to get this one? So this will be useful. This kind of thing will be useful for us to compute it. All right. So if the conclusion of at the end of the afternoon class, the professor said that it's a bad lecture, so what's the chance that if the morning lecture was also bad? So this basically is just translate the given questions. All right. So given that, what happened? What is the chance that it give a bad lecture in the morning? So from what the professor said, we know that the B has occurred because they say there's a rotten class, a lecture. All right. So B has occurred. So what's the chance that A has occurred? So this translated is, yes, we know that B has occurred. And what is chance that it got a bad lecture? So we are asked about this probability. So the point is you should be able to translate a word question into a probability statement. And the probability statement, in this case, we define what is A, what is B, so we know what is A complement, what is B complement. So this question means that, okay, if we know that B has occurred, so condition on B, what is the chance that A has occurred? All right? So we call it A given B. So we apply the definition or using the answers we obtained. Oh, by the way, this one and this one look similar, right? Are they equal? Similar does not mean they're the same, right? You cannot switch the order. It's not A intercept B. A intercept B is the same as B intercept A, so they're commutative. A condition on B, condition on something, all right? Which is the part A is condition on A, while the part E is condition on B. They're totally different conditions, so they are not the same, all right? And if you like mathematics, look at the definition. Part A is probability A intercept B divided by probability of A. The denominator is probability A. While for part E, the numerator is the same, probability of A intercept B, but the denominator is not the same. It's probability of B. All right? When I say not the same, it means that maybe by coincidence, the two probabilities is equal to the same numeric values. But in general, we don't expect if the morning is a bad lecture, the afternoon will have the bad lecture as well. We don't assume that. So we assume that they're different. So A and E, the answer are different. All right? So here is how you get the answer. It's quite straightforward. All right? So you can see that. All right? Okay, I want to highlight this one. Think of it. What is probability of B? Huh? 0.2, am I right? That's given, 0.2, 20%. So in other words, if I have no information about what happened to the morning, and the chance that the professor will give a bad afternoon lecture is 20%, given in the question. But now, if I know that in the morning he gives a good lecture, then the chance of probability of giving a bad lecture given a complement, that means he gives good morning lecture, the chance reduced to 1/7. 1/7 is what? 1/7. Right. It's less than 0.2. Less than 0.2. So in other words, if we have some information about what happened to the morning, then we predict or we will think that, yes, afternoon will have a slightly better lecture. I mean, chance of getting a better lecture. So the chance reduced from 0.2, 20%, to 1/7. All right. 1/7 is roughly about 0.14 something or 0.15, 15%. All right. So this is how you get the D part, and E just follow from the definition. All right. So again, you can see that if we know that afternoon is bad, then it's likely that in the morning it's also a bad lecture. It's 50%. But if we don't have this information, just look at the chance that it gives a bad lecture in the morning, then the chance is 0.3. 30%. All right? So what does that mean? It means that whatever happens in one of the sessions, it may change our belief in the probability of giving a bad lecture in another session. All right. Now, if they're totally unrelated, then we call it independent. What happens in the morning does not affect what happens in the afternoon. So whether it is a bad lecture or not, we still have the same probability of a bad lecture in the afternoon. Then in that case, the two events are considered as, we call it, independent events. Independent events. All right? Okay, so now we follow the definition of conditional probability and get this called multiplication rule of probability. It basically just rearrange the definition of conditional probability to probability of A intercept B, all right, divide by probability of A equal to this conditional probability. I just moved the probability of A to the other side of the equation, provided that probability of A is not 0, and provided that probability of A is not a negative number. But equal is okay. We are not talking about inequality. So either one of them is true. But now the interpretation will be like this. Okay, the first one, you are thinking of what is the chance that A has occurred. So it's probability A. And then look at what is the chance that B has occurred, will occur, given that A has occurred. All right? So in other words, if you want to occur, the two events occurred, then you just look at one occur first and take the second event, all right? Take another event as the second event, conditioned on the first event being occurred. So the first line, we treat A as the first event. Second line, we treat B as the first event. Are there any difference? No difference. You can use it whenever you find it is convenient. All right? Both are correct. Which one comes first? Depends on the questions, depends on the information that you have, then you apply the one that is easier for you to use. So it's the probability of getting two events. Now, so in order to calculate the probability of A intercept B, now we have two ways to do it. In fact, there's a third way. What is the third way to get this probability of A intercept B? We learned it counting. Count the number of sample points corresponding to A intercept B. Divide by the number of sample points in S. So that will give you the probability of A intercept B. Okay, so this is to translate the above statements. One is probability of both events occur, all right, A intercept B, and A and B. Intercept means and, A and B, both events occur. Okay, event A and event B, that's the English phrase. All right, it's equal to the product of one event occurs first, and then times the conditional probability of the other event. So if this is event A, then it is probability of event A times the conditional probability of the other event B given A. All right? All right? So that is what we mean by multiplication rule. It can be probability of B times probability of A given B. So we extend this to 3 events. So we want A, B, and C occurs. So you do it step by step. So you can have A occur first, probability of A, times probability of B given A, then times probability of C given A and B. All right? It doesn't matter. You can have C first, and then followed by A, and then followed by B. All right? It doesn't matter. All right? Provided that probability of A intercept B is bigger than 0. But from here to here, I need to have probability of A greater than 0. How do I know probability of A is greater than 0? Again, if you remember properties of probabilities, A and A intercept B, which is bigger? Which one is a subset of the other? A is a subset of A intercept B, or A intercept B is a subset of A? A intercept B is smaller because it needs to have both in A and B. All right? So anything in A and B must be in A. But something in A may not in A intercept B because it may not in B. All right? So A is a bigger set. So of course, if probability of A intercept B is bigger than 0, probability A must be bigger than 0. Why? Because probability A is bigger or equal to probability of A intercept B. All right? So in other words, it understood that once probability of A intercept B is bigger than 0, then probability A is bigger than 0. For a lot of us, we don't bother, don't care, right? We just write it down. But it's very crucial that you make sure that the conditions are the same. The first two products require probability of A bigger than 0. But we already state probability of A intercept B is bigger than 0, which automatically implies probability of A bigger than 0. So we don't have to worry about that. All right. Okay, so this is the general statement. All right. A1 and A2 up to AN is equal to 1, the product of all these probabilities. Provided that the intersection of all this A1 up to AN minus 1 is bigger than 0. All right, so here are some example. So I have 12 shirts, 3 are white, and I take out 2 shirts, 1 by 1, without replacement. All right? So this may be easier to work on using conditional probability. So we are asked, what's the chance that both shirts are white? By the way, we have to define our events. What are the events? And this is very important. If you get the events wrong, then you may have problems getting the probability of such events, and also the probability or to get the answer to your questions. All right? So, what are the events that we need to consider? Okay, let's look at the second question. What is the probability that only one white shirt being picked? All right. Okay. Oh, we also have C. If 3 shirts are chosen at random, what is the probability that all are white? All right. So how do we define the event? So the question says you take one by one. So you can think of it, take the one shirt from this altogether 12 shirts. All right, take one out. So the event that we are considering, all right, it's not just one shirt from 12 shirts, but instead it is a white shirt being chosen in the first shirt that you draw. All right, that you select from this group of shirts. All right, that is how we define it. Think of it like this. We are talking about select shirts. We have 2. We take one by one. So the first event is something to do with the first shirt that we choose. All right? So there are only two possible scenarios. One is a white shirt. What is the other one? A black shirt? We don't know whether it's black or not. So we put it in a general term, non-white shirt. All right? White and non-white. It covers everything. So all these 12 shirts must belong either to the white shirt group or non-white shirt group. So don't laugh at this. It's very useful. So we cover everything. All right? So here's how we define it. A1 as the event that the first shirt is a white shirt. A2, the second shirt is a white shirt. If you like, you can have A3 being the third shirt is a white shirt. All right? But we may not need to go that far. Okay, so what's the chance that you're getting A1? So that means among the 12 shirts, there are 3 of them are white. All right, so the chance is 3 over 12. How to get 3 over 12? Why is it 3 over 12? You never thought about it, right? 12 shirts. A. If the white shirts are big for giant, the other non-white shirts are for baby. So you go and take. So maybe it's not equally likely. All right, so here make assumption that each shirt are equally likely. So we draw it at random and we assume that they're equally likely. So we have 12 sample points, 12 shirts. And there are 3 out of these 12, 3 of them are favor to this A1. So that's why it is number of sample points, which is 3, over the total number of sample points. All right, 3 over 12. All right, so that's why you need to ask questions yourself. So what happens? They are not equally likely. One big shirt, one small shirt. Non-white shirt is small, so they're not equally likely. Then you have a different story. Here we assume that they are equally likely. So it's 3 over 12. But how about A2? How about the second shirt is a white shirt? Oh, you taken one. Then the second one must be 2 white shirts left and out of this 11 shirts. So, probably A2 equal to 2 over 11. Is it correct? Of course, I already written down. So what is probability of A2? Does it equal to 2 over 11? The 11 shirts, you have only 2 white shirts. Right? Is this probability A2? No. Hey, think of it. This is only 2 over 11 is only valid if the first shirt that you select is a white shirt. What happens if the first shirt is a non-white shirt? You have 11 shirts left, but you still have 3 white shirts among these 11. So the probability is different. So, which one is correct? Which one is correct? None of them. Both are wrong. All right? Why? Because 2 over 11, you obtain it based on the assumption that the first shirt drawn is a white shirt. So in fact, this is not probability of A2, but instead, this one is probability of A2 given A1. Right? How about this one? This one is probability of A2 given A1 complement. That means the first shirt that you select is a non-white shirt. So you still have 3 shirts, 3 white shirts out of the 11 shirts, remaining 11 shirts. All right? So what we are asked in part A, first and second shirts are white. So it is A1 and A2. So it's A1 intersect A2. All right, so the answer is 1 over 22. All right. Now, what is the chance of probability of A2? Probability of A2. So, I see A2 here. I also see A2 here. One is conditional A1, the other is conditional A1 complement. Can I just add these 2 probabilities together to get the probability of A2? Let me repeat it again. I want to get the probability of A2. I see one conditional A1, which is 2 over 11. I see condition on A1 complement is 3 over 11. So how do I combine them? Add. Is it correct to add them? So you ask yourself, can we add these 2 probabilities? Forget about the numbers. Just look at, can we add, what does it mean? So it's not right. In fact, if you remember at the beginning I mentioned about this, you can think of it like this. You need A2, right? I want to find the probability A2. But A2 consists of the part come from A1. And what is the other part? What is the other part? A2 and A1 complement. Combine these 2. And they are exclusive events. So you just work on these 2 probabilities. Probability of A1 intersect A2 and probability of A2 intersect A1 complement. So you still need those 2, but you have to modify it. All right? So you have to multiply 2 over 11 by the probability of A1. Then the second one, you have to multiply by the probability of A1 complement. In order to get this probability, you have to multiply this by probability of A1. In order to get this probability, to multiply this with probability of A1 complement. Multiply, I shouldn't. Okay, multiply. So you got the intersection of the 2, and then combine them. We'll come back this later. All right. But I just want you to make sure that you understand the consequences of this condition thing. So condition will change a lot of things. All right, they are not the same. All right, part B. So we want to calculate probability A2, right? This is what we just mentioned. So the answer is 9 over, right. So, okay, sorry. This one is not one. Okay, what was the question, part B? What is the probability only one white shirt? So one white shirt. One only. So this means that the first one is a white shirt, the second one is not a white shirt. So it's one white shirt. But you can also have the second one is a white shirt and the first one is a non-white shirt. All right? And just combine them. Now, so you can work this out. Obviously, they are independent. Sorry, they are mutually exclusive. Why they are mutually exclusive? Because you cannot find some elements which common to A2 complement and A2. So the intersection is empty set. So they are mutually exclusive. So you can just add up the two probabilities together. And then I break down using the multiplication rule, and then each one I work it out easily. So I got the answer. It's 9/22. All right? Now, you can check. This one, all right, is equal to, all right, this is A1 union A2. All right? Probability of A1 union A2 minus probability of A1 intersect A2. It's the same answer. It can be proved. You think of it, the first one is the chance that you get one white shirt as the first one and one white shirt as the second shirt. And it can happen that both first and second are white shirts. So I have to eliminate this double counting. I don't ever exclude this part. You can think of it like this. But I can prove mathematically. So this is A1, this is A2. I want only one shirt. That means this part and this part. So obviously it's the union without this part, which is common to both A1 and A2. So I have to subtract this part. All right? But of course, you may need to understand on how you got this one. All right? Proof mathematically. Don't draw a Venn diagram. Venn diagram cannot be used as a proof. All right? So you have to use this operation of events that we discussed in earlier sessions. All right? But anyway, maybe this one is easier to do. All right? Easier to do. And this is very explicitly, it's saying that first shirt is a white shirt and the second shirt is a non-white shirt. The other event is that the first shirt is a non-white shirt and the second shirt is a white shirt. So there's no two white shirts. I just combine these two, union of these two events, and they're mutually exclusive. And work out the probability of each of these. Okay, the third one, now I introduce the third, A3, the third shirt being a white shirt. All right? In order to have all three together, I have to multiply all this. So the first one is 3 out of 12. I have 3 white shirts out of 12 shirts. So after the first shirt is a white shirt, the second one as a white shirt, the chance is 2/11. Because I have 11 shirts left, and out of these 11 shirts, there are only 2 are white shirts. Then finally, I have 10 shirts left, and there's only 1 among all these 10 remaining shirts. So multiply them together, this is the chance that I got all the 3 white shirts. All right. Okay, so I skip this example 2. Example 3 also, I think you can read it. Okay, example 4. Example 4. Okay, for example 4, we are given that a doctor, all right, correctly diagnoses a particular illness is 0.7. These figures are not real data, so don't treat it seriously. It's just a number that we use. So a doctor can find out that, okay, you have this disease correctly only 70% of the time. And, okay, if the doctor makes an incorrect diagnosis, then the patients may enter a lawsuit with 90% chance. All right? So you must understand what are the events we mentioned here. One event is that the doctor, okay, diagnoses correctly. So that's one event. The other one is enter a lawsuit. I mean, the patient will sue him. So to translate it, what's the note? Yeah. So I use D as correct diagnosis, and U means the patient sues. All right. So in other words, what I given is that probability of correctly diagnosis is 0.7, probability of entering a lawsuit, while given that is incorrect diagnosis, is 0.9. So you must able to identify the events in questions. Here there are two. One is whether diagnosis correctly or not. The other one is being sued or not. But we are not given the probability of being sued. But instead, we are given that if incorrectly diagnosis, then the chance of entering a lawsuit will be equal to 0.9. Then we are asked, what's the chance that the doctor makes incorrect diagnosis and the patient sues? So in other words, we are asked to find this probability. All right? So everything seems so easy once you identify them in terms of probability statement. How to find this probability? So this one is equal to, by the product rule, is probability of D times the probability of U given D complement. Or is equal to probability of U times probability of D complement condition on U. These two are different ways of getting the probability of U intercept D complement. Are they this? I mean, which one should we use? Or can we use either one? Do we know probability of U? We are not given. So if you want to use the second formula, you have to figure out what is probability of U. Not only that, you also have to find out what is probability of D complement given U. Hard, eh? How about the first one? Do we know probability of U given D complement? Yes, it's given 0.9. How about probability of D complement? Do we know? It's not given, but we can compute easily. Why easily? Because it's just 1 minus probability of D, and we are given probability of D. Right? So probability of D is 0.7, so probability of D complement is 0.3. So it's very easy. So this is the answer. All right? 0.3 times 0.9, so it's 0.27. All right? So the point is, first of all, identify the event. Once you identify an event, like for example, correct diagnosis, then automatically there's a D complement, which is incorrect diagnosis. Sue, enter a lawsuit, or not entering a lawsuit. So once you define U, there's a U complement. And then try to express all these events or probabilities in terms of a probability statement, and link the information given to you to these probabilities. And then apply the formulas that you learn or properties of the probability, try to figure out. All right. Some are easy, some are difficult. All right. So like the second expression here, to compute this probability using this one is much harder. All right. Why it's harder? Because we are not given the information. While if you use the first expression, then it's easier because almost all are given to us. All right, question 5, example 5. So we have 4 individuals respond to a request by blood bank for donations. So all of them forget about their blood types. Not in Singapore. In Singapore, if you have an IC, we still have a blood type in the IC, right? Do we? No. Oh, okay. Mine has a blood type. Yeah, I belong to the old generations, right? Okay. Okay, suppose only type A plus, all right, is one, and only one out of these four actually has the type. We don't know who has this A plus type. Huh? You have the blood type, your IC. Huh?
The green IC.
What green? You have green IC? Huh? Not red, not pink. Not pink, not blue, I mean, sorry. Pink and blue, right? Green is only for those in the serve the nation, then you have the green IC. Right? I talk too much, right? Exposed, right? Everyone knows the facts, right? Okay, so now a potential donor select at random. So I have four, I select one of them, all right? Test it. So whether it's A plus. If it's A plus, is that the blood bank want? Then I stop lah. Okay, the other three can go home. All right. Maybe they are A plus also, but no, sorry. Only one has. Only one has. So so we don't care about the others. Once I find an A plus, the rest can go home. All right. So now, so we select at random. What is the probability that at least 3 individuals must be typed to obtain the desired type? At least 3 individuals. What does it mean? It means that you select one. Sorry, this guy is not A plus. If it's A plus, then it does not fit to this description. All right. So the first guy must be non-A plus. Then we take the second guy. Again, the second guy is not A plus. All right. So that means if assume that A1 is the first guy is not A plus. I mean, what's the one that I use? A is non-A plus for the first one. B, maybe I should use A1, A2, but here I use B. The second donor is not A plus. All right? So, at least you need 3. So that means what? Do I need a C? The third donor is not A plus. Do I need that? In order to answer part A. Part A means at least 3. First one, sorry, not A plus. Second one, A plus. Then if the first two are not A plus, definitely you will go to the third one. All right? If the third one is not A plus, then you have to go to the fourth one. All right? So that means you will either test 3 or 4 of them. If A and B occur, that means you couldn't find an A plus in the first and the second person. What I'm trying to tell you is that although the question say at least 3 of these donors has been tested or typed, but you translate it, you just need to find the A and intercept B. A and B occur. First one non-A plus, second one non-A plus. That's it. If this A and B occurs, automatically you will go to the third or even fourth. All right? So we just multiply the 2 together. So the first one, 3 over 4, because there are 3 persons with non-A plus. Then the second one is 2 over 3, because we select one non-A plus. So among the 3 left behind, there are only 2 is non-A plus. So it's 2 over 3, so multiply them together, so you get the answer 1/2. All right? So in other words, there are 50% chance that we will need to go to the third and or fourth. We have to test 3 times or 4 times in order to find the right donor. All right. In fact, what is the chance that you need to find to test for the 4th person? What I mean is that once you test first one non-A plus, the second one non-A plus, the third one non-A plus, you left with only one. That must be an A plus. All right? Okay? Okay. The third donor is A plus. So you need the first one not A plus, second one not A plus, all right? And the third one is A plus, given that the first 2 are non-A plus. So the answer is 1/4. So it simply means that it's A and B, non-A plus, non-A plus, and maybe C is, the third one is non-A plus, so I need C complement. So the third one is A plus, given that the first two are non-A plus. So therefore, after the first two, there are two donors left, and out of these two, one of them is non-A plus, and one of them is A plus. So that's why you have to multiply 1/2. So the answer is 1/4. All right? You have to understand that although the question asks you to find the third donor being A plus, all right? So how to find it? It's easier to use this condition probability. That is, in order the third one to be A plus, your first one has to be non-A plus. The second one has to be non-A plus. And then the third one is A plus. So how to get these three events together? All right? So we work out using the conditional probability. Now let me ask you, can I use the combinatoric, the counting method, to get the probability of the third one being tested is A plus? So in other words, you have to write down order 4 tuples, a vector of 4 entries, all right? And then identify whether it's A plus or non-A plus for each entry, all right? And then try to figure out. That means you try to arrange in order. In this case, the order has to be considered, all right? So let's say I have individuals, subjects, 1, 2, 3, 4, all right? And only 4. Let's assume that 4 is the A plus. So you may have 4, 1, 2, 3 in that sense, all right? So okay, it's a little bit more complicated because if once you identify A plus, you won't go for the next 1, 2, 3, all right? So the counting method may not easily compute, all right? So you better use the conditional probability. All right, okay. Law of total probabilities. The name is very, very high sounding, total probabilities. But what it says is very straightforward. It's simply saying that I partition the sample space into many mutually exclusive and exhaustive events. What does that mean? It means that I partition into subsets so that if I put all these subsets together, union them, I will get back the sample space, S. But each of these subsets are not overlapping. That's what we call mutually exclusive. All right? Called exhaustive means that we put all this together, I will cover the S, the sample space. All right. So then the probability of B is equal to probability of B intercept AI. Is quite straightforward. I have a B. I look at this part of B belong to A1. Look at this part of B belong to A2 at the same time. This part of B belong to A3 and so on. And I put all this A-intercept BI together. That will be my B. Right? Here's the picture. As this is A1, this is A2. Unfortunately, it's not well drawn. Right? Okay. Up to AN. So, no overlapping, and combine all this is equal to S. All right, then this is your B. So, the part of B comes from A1, this part. The part of B comes from A2. Maybe I should change the color. Pen, color, ink color. Right? This is part. Oh. Yeah. Brown is not good, huh? blue. This part, and the others, and finally come to this part, which is common to B and AN. Put all this together, and that is your B. Then apply the, go back to red, okay? So then you can see this one, sum of all this probability, and each one apply the multiplication rule, then it's probability of AI times probability of B given AI. All right? Now, okay, right? But can I write it like that? Is this correct? Correct, right? Am I right? Each of one is equal to probability of B times probability of AI given B, right? Correct or not? Then, is there any I here? No I, right? What does it mean? It means that every terms in this summation sign will have this factor. We call it common factor. I can bring it out of this summation sign, right? So this becomes probability of B, sum of probability of AI given B, right? AI given B, all right? But then what does it mean? The sum of all the AIs is equal to the sample space, right? Sum of the probability of AI given B is the same as probability of S given B. This becomes probability of S given B, which is equal to 1. What does it mean? It means that on one side it's probability of B. If you use this approach, you also get back to probability of B. All right? It's identity. It's always true. All right. So my point is, depends on how you break it down. All right? We want to calculate probability of B. So we look at B common to A1, B common to A2, and look at the probability. If you treat it as probability of B times probability of AI given B, then you just go back to your square, go back to what you want to find, and does not help you to find anything. So you better use this one. So that's total probability. All right. Okay, let's look at an example. Ooh. Okay, we have 3 machines, A, B, C. Each produce 2%, 1%, and 3% defective screws. All right. Now, at this point, what are the events mentioned here? Is machine, which machine that the screw from. And there are 2 types of screws. One is defective, the other is non-defective screws. So we are looking at 2 events, or 2 types of events. One is machines. In fact, there are 3 machines, machine A, machine B, and machine C. Do we have machine D? Of the total production, machines A, B, C produce 35%, 25%, 40%, respectively. And this is important. It's simply saying that we only have 3 machines. How do I know that there's only 3 machines? Of course, it says that the total production, all right, 35% come from A, 25% come from B, and 40% come from C. Add these 3 percentage together. Is it 100%? If it's more than 100%, then it's wrong. How can a total production, this machine A give so many and B and C, add together is more than 100%, can never more than 100%. But can it less than 100%? Can, right? Provided that there's another machine or another way to get the screws, which is not mentioned. All right? But here, luckily, it adds up to 100, so we have only these 3 possibilities. The screws are produced from machine A, or B or C. No other ways to get the schools. All right? Because they add up equal to 100%. Then we select a school randomly. What is the probability that it is a defective? And what is the, if it is produced, is a defective, what is the chance that it comes from machine C? All right? I know that some of you like this tree diagram. Okay, tree diagram useful, but just help you to get the answer. All right. If you construct the tree diagram, what is the first stage? Stage 1. Is it a screw, a defective screw, or a machine? Naturally, you start producing the screw. So start from machine. Machine A, machine B, and machine C. So if you use tree diagram, start from a node. I don't know whether you know how to construct a tree diagram. Start from a pond. I call it node. Branch. And in this case, branch machines. So it's machine A, B, and C. Only 3 machines in these questions. Then each branch associated with a probability. So what is the chance that it's produced by machine A? The chance is 0.35, 0.25, and 0.4. Make sure that the probabilities on all these branches from one node had to add up equal to 1. All these 3 numbers add to 1. And this branch represents the probability of getting from machine A. Then the second stage is whether the screw is defective or not. Okay? So there are only 2 possibilities. One is a defective screw. The other one is a non-defective screw from machine A. So this one, all right? What is it? What is this probability? Huh? 2%? Is it correct? What does this branch mean? It represents a probability. The probability go to D. That means defective screw. From where? From A. So that means it's conditioned on A. So what is the chance that you got a defective screw from machine A? Do we have that number? Do we have that probability? We have 6 numbers only. So, is it given? Yes. And what is it? 2%. From machine A, 2% defective. So this is 0.02. Oh. 0.02. Then what is this one? 0.98. Because the 2 have to add up equal to 1. So in other words, from machine A, 98% of the screws are non-defective. So once you reach this position, this knot, all right, then it's simply saying that this is a screw that goes from machine A and also is a defective screw. So it's A intersect D. This one is A intersect D. This one is A intersect D complement. So you can construct for the rest of the tree. All right? Now, we are asked what is the probability that it's a defective screw. So this gives you defective. This also gives you defective. And this also gives you defective screws. All right? Are these defective? In fact, they are not just D. They are D intersect A, D intersect B, and D intersect C. So you just have to add these 3 probabilities together. How to get this probability? You have to multiply this and this together. All right? So probability of defective, it is probability of D intersect A plus probability of D intercept B plus probability of D intercept C. This means defective screws from machine C. So it's equal to probability from machine A times probability of D from machine A, and so on. All right? So that's how you get the answer. So here it is. All right? So this is the answer, 0.0215. So in other words, the chance of getting a defective screw is only about 2.15%. But if we know that it is from machine 2, then only 2%. Sorry, from machine A, then only 2%. From machine B, I think it's 1%, right? From machine B, 1%. Machine C is 3%. But if we don't know which machine it's from, then in general, we combine all this, then it's 2.15%. Second part, so given that it is from machine D, sorry, it's a defective item, what is the chance that it is from machine C? Then we will apply the conditional probabilities, then we get the answer, which is 0.5581. All right. So in other words, if we select a screw from a machine and we know that the chance, this is a defective screw, then it's more likely that it's from machine C than from other machine. All right? But if you just select a screw, then the chance that it is from machine C is about 45%? So it's less than that number. So in other words, if you know that it's from it's a defective item, it's more likely that it's from machine C than if you don't know anything about the screw. You just pick one screw. What's the chance that it's from machine C? All right. The probability of C, which is this one, this is the chance from machine C, 40%. All right. Just select one item, one screw from this production, then there are 0.4 or 40% chances from machine C. But if we look at it, it is a defective item, defective screw, then it's likely that, or it's a 56% chance that it is from machine C instead of only 40%. All right? Okay. So, example 2. Okay. So we have 2 beds. One consists of 7 balls, 4 white and 3 black. The other consists of 8 balls, 3 white and 5 black balls. We take one out, don't check what color it is, and put it in the second bed. Then what is the chance that now the ball taken from a second bed is a black ball? So, okay, let AI is the event that ith ball drawn from the a white ball drawn from the ith bed. So AI complement is the black ball drawn from the ith bed. All right. So probability A1 is 4/7. So probability A1 complement, that means take a black ball out of the first bed, because they have 3 black balls, so it's 3/7, or 1 minus this number, because there are only 2 types of balls, black and white. All right. So a black ball simply means that it's a non-white ball, because there are 2 types, 2 colors only. Then, if it's a white ball taken from the first bed, all right, okay, now there's no way that you can compute this directly. You have to condition that, okay, because we don't see the color of the ball taken from the first bed. So let's assume that it's a white ball. Then we put in the second bed. So now, if this occurs, then now of the nine balls, you have 4 white balls. All right? Now what happens if the ball you drawn from the first bed is not a white ball but a black ball? You put it inside the second bed. So now altogether you have 9 balls, but out of this, there are altogether 6 black balls. All right. So under the law of total probability, I can compute the probability of a non-white ball. That means a black ball taken from the second bat. All right. So we look at the chance that the first one, the ball taken is a white ball. There's this one. Or the ball taken from the first bat is a black ball, so it's this one. So we multiply these two probability and add them up. So that's the condition. So this is the total probability. The chance of A2 complement, there are two ways to get A2 complement. One is A1. That means the first ball or the ball taken from the first bat is a white ball. Or the first ball taken from the white bat. The ball taken from the first bat is a non-white bat, a non-white ball. Yeah. This color thing. Okay. Example 3. Okay. So traffic police work to enforce speed limits by using a speed camera in 4 different locations. Okay. The speed camera at each location operate 40, 30, 20, and 30% of the time. Does all this number add up to 100%? It's not 100%. Why? Why is not add up to 100%? Okay. Don't think of it as one camera, one speed camera. So maybe it's installed on a vehicle or a van and then move location 1 30% of time and then 20% of time in location 2. Then you may add up to 100%. You have only one van, one speed camera. It's either in location 1, location 2, 3, or 4. But now we assume that we have 4 speed cameras. Each camera will operate or not operating. So in location 1, L1, then only operate 40% of chance. All right. I don't know how true it is. Maybe in Singapore, don't bet, maybe operate 100% of the time. All right. So you speed, then it's speed. All right. So they take photo and find you. All right. But here we assume that the camera only operate in certain percentage of the time. And this guy also have speeding on his way through all these 4 locations, but with different probabilities. All right. Okay. So, what is the probability that he will receive a speeding ticket? All right. So, now think of it. He will issue a ticket only when he's speeding, and the camera in operation at that location, that point of time. All right. Otherwise, if he's speeding, all right, but the camera is not in operation, then he will not be caught. So now the question is that you must translate all this into a statement, probability statement. All right? So let's assume that the event that he received a speeding ticket is B, and A is that he passed through certain location. All right? So in other words, he received a ticket maybe from location 1. He passed through this location. All right? And passing through second location and so on. All right? So he received a ticket only when he passed through this location and he received the ticket. And when will he receive a ticket? He passed this location only when he speeds, right? But he, okay. I think the description is not quite right. I'm sorry, I have to adjust the description of A1. It's not just pass. It's speeding at that location. All right, sorry about that. He's not just pass. He speed through the location. All right. So you have to change this. All right. So what it means is that in order to caught that he's speeding, he must pass through that location. Must speeding at that location. At the same time, the location, the camera in operation. All right. So this is the probability that he's speeding at location 1, and this is the probability that he will issue a ticket. Issue a ticket. When will he issue a ticket? Only when the camera is in operation. So only 40% chance that the camera is in operation, so therefore he will issue a ticket. All right? If he passed that location speeding. So the chance that he will receive a speeding ticket is 0.27. Right. This one change, he passed, he's speeding back, right? Through the location, he speed. Okay, then if he receive a ticket, what's the chance that he got it from location 2? That means he's speeding in caught in location 2. So you just apply this one, and so it's 1/9 of the chance that he got this because he passed his speeding at location 2. It's 1/9 chance. So what is probability of A2? Of the A2 is 0.1. All right. He's speeding on location 2 with 10% chance. But now if he receives a ticket, then it's likely that, all right, it slightly increased the chance to 0.11 to 11% instead of 10%. All right? Example 4. These examples are quite interesting. So we have 3 coins. In order to differentiate, there are different coins. So one is 50 cents, 20 cents, and 10 cents. Then we have a fake 10 cents coin with 2 heads. The other 2 are normal one with 1 head and 1 tail. So now we choose a coin at random and toss it 4 times. And then if we see 4 heads, okay, so what is the probability that it is a fake 10 cents coin? All right? So we have different coins, 3 of them. All right. So let A be 10 cents coin being chosen, B 20 cents coin chosen, and C the 50 cents coins being chosen. So translated, we are asked, what is the probability that if we have 4 heads, and what is the chance that it is a 10 cents coin? All right, A. So what is this probability? All right, once you choose it, you toss it. Now, so what is the probability of getting 4 heads? What is the probability of getting 4 heads? Is this correct? It's for a fair con. This is correct. 1/2 times 1/2 times 1/2 other half. But now the situation is that we select a con from these three. Now, if all these three are normal cons, then it's still okay. All right? But the problem is that it's not. So it depends on which con you select. So in other words, the probability of 4 heads, given that it is a fake con, it's a 10 cents fake con with 2 heads, then this probability is equal to 1. Both sides are head. So no matter how many times you toss it, it's always head. So getting 4 heads chance is 1. How about the others? If it is a 20 cents con, it's a fair con, a normal con, then the chance is 1/16. 1/16. All right? Because it's fair. So how to get head? You may get head, tail, things like that. So the chance getting 4 heads together is 1/2 raised to power 4. Similarly, for 4 heads, getting a C. So, getting a 4 head, it can be from A, can come B, can be from C. So you have to work out the joint probability. So, this is how we do it. So this is the probability of getting a 4 head given A, and probability of getting a 4 heads given B is 1/16. Probability of 4 heads given C is 1/16. Then you ask yourself, what is the probability of getting a 4 head? Then it will be probability of 4 head given A, or intercept A, plus probability of 4 head intercept B, plus probability of 4 head intercept C. That means getting 4 head from a 10 cents con, or 4 heads from a 20 cents con, or 4 heads from the 50 cents con. And this is important, because in order to compute this probability, it is probability of A times probability of 4 head given A. This one, we already say that is equal to 1. But what is this one? This one is equal to 1/3. Why is it 1/3? Because we are supposed to choose randomly one of these 3 cons. All right? But if it's not the same probability, then we may have to adjust this. But here we assume that they are equally likely being selected. So the probability of getting 4 head is equal to 3x. So it's not that small chance, because you have 1/3 chance to get a con that will sure give you 4 heads. Well, if you select the other 2, the chance is very small of getting 4 heads. So as a whole, the chance of getting 4 heads will be 3x. Then ask yourself, so what happens if the 10 cents con is fake, the 20 cents con is also fake with 2 heads? Then what is the chance of getting 4 heads? Or the other way around. All right? If the 10 cents con is 2 heads, but the 20 cents con, this time no 2 heads, but 2 tails, right? And the third one is a fair con. What is the chance getting a 4 head? So you have to work it out. All right? Okay, so given it's 4 head, what is the chance that it's from A? So it's very likely that it's from A. Otherwise, you won't see 4 heads. So if you see 4 heads, then it's likely that the 10 cents con, that means the fake one with 2 heads, is being selected. That's why you have see something which is not so common, but it happens, and you suspect it may be not a fair con with 2 heads. All right? Bayes' theorem. You may heard about this Bayes' theorem. There's a branch of statistics called Bayesian inference. So it's something to do with this Bayes' theorem. So what Bayes' theorem says is very, very simple. All right? So it's saying that, all right, if you recall, look at this. Where's my total probability picture? Here. All right? Now, total probability is saying that the chance of getting this red part, the B, consists of combine all these probabilities of this intersection of B intersect AI. All right? Now, the Bayesian theorem is saying that, okay, if I know B has occurred, that means I know that what happened must part of this red. Then I asked whether it is from A1. What's the chance that it's from A1? Or A1 has occurred. That means I know, yes, B has occurred. So how likely A1 has occurred? I ask this question. Now, if you use the conditional probability, it's nothing new. It's just like this. All right? A1 intercept B, given conditional probability of B. All right? So this is what Bayes' theorem is saying that. All right? So I would like to draw the tree diagram. So this is from A1, where is the chance it got B or B complement? From A2, B and B complement, and so on. All right? So now, I know B has occurred. So it can be from here. I know it's B. I know it's B. But I don't know which path it reached this B. So I'm asking, what is the chance that, okay, I know that it's B. What is the chance that it goes through one of this path? What is the chance that it goes through A1 to reach B? So what is this probability? This means that I know something at a later stage. If I say B is a later stage, the second stage, I know what happened in the second stage. I want to go back to look at what is the chance that in the first stage, it comes from this particular event, this particular branch. All right? So if you recall, just now we talked about machine. So usually it's a machine that produces the screws. Then we look at the second stage, look at the screw, whether it's defective or not. So now the Bayes' theorem saying that, okay, if I know I take one screw, okay, it is a defective screw or a non-defective screw, then I ask whether it is from machine A, machine B, or machine C. Like the general approach is that you start with the machine produces screws, and then it has these screws, production of screws, and then whether it's defective or not. But now I pick one and know that, okay, it is non-defective. What is the chance that it is from machine A? So we ask, go back to the previous stage to ask what happened, or what's the chance that it happens like that in the first stage. That's what Bayes' theorem is about. But basically, it's just a conditional probability. All right? Okay, so So, yeah. So, it is like this. It looks very complicated, right? But if you recall, this is nothing but just probability of B. Then this is just basically go back to our conditional probability, right? So don't be frightened by this complicated formula. We already done it. This is called total probability. The chance of getting a B comes from B common to A1, B common to A2, B common to up to AN. And then we put all this together. That is the total probability. The denominator in the Bayes theorem is the total probability. All right? I don't think I have time to go for examples, so I will start it this Thursday. All right? So remember to go for your tutorial. The tutorial starts this week. All right? Okay, we stop here.